Hello everyone, and I'm back again with another video. My name is Antoinette C. Pahanoy of ECE 3A, and today I'm going to discuss to you a topic for my performance task number 3 in my subject at ECE 23. Right now, let's go ahead and start. I have here a quick definition of natural sample PWM or pulse width modulation. So it's traditionally an analog technique where the input signal is naturally sampled by a carrier triangle waveform at the instant of switching edge. It can react instantly to changes in input command and produces no attenuation or distortion of the synthesized waveform. Pulse width modulation is based on simple fact that the mean value of two-level square wave is proportional to its duty cycle. Thus, any signal can be modulated as a square wave by ensuring the duty cycle always corresponds to the signal instantaneous value. All right, I have here a example of the waveform of the natural sampled PWM. Also, I'm going to discuss to you to be specific about NBDS because that is what is being assigned to me. So that will be natural sampling single-sided or levels BD. So that's how it means. It's a abbreviation. So a simple approach, NBDS, is based simple superposition since NBDS can be synthesized by 180-degree phase shift of the modulating signal to the opposing modulator. So in definition of natural sampling and single-sided, I did put in how that was described, or the sampling refers to the amplitude representation in the modulating process. So quite simply, analog signals results in natural sampling. For the single-sided, can be performed with ascending or descending sawtooth carriers. So that's how it is being defined for the two of them. Now, I have here an overview or at least an explanation on how does NBDS works. An example for NBDS for natural sampling is class BD switching. The use of a four-device full bridge configuration permits the uses of class BD depicted in this figure on the left side. And the driving method of achieving this three-level modulation, the two devices on the left, the side marked A, as what you have seen there, and are switched exactly as described for class AD. However, the devices on the right marked B, as what you have noticed here. So although still complementary to each other, are no longer the simple complement of the A side. Instead, the B devices are driven by a modulator driver derived from an inverted version of the audio signal. The effect of this is that the B side switching mode, or node waveform is inverted in time with the sampling period with respect to the A side waveform. Now, this is also an example provided to us by our instructor, so the time domain signal characteristics of the NBDS are shown in the figure. The existence of high frequency common mode signal, that what you see here, and also at the bridge phases where it illustrates the necessity for common mode filtering. So common mode means that it's a signal where it flows on the same direction in the pair of lines. While the differential mode is what you have noticed here, that the pair or the signals are flowing on opposite direction in the pair of lines. And you can already see here what's happening because up until on the middle, it changes. So it's going to the opposite direction. For the common mode, it's just flowing at the same direction or of the pair of lines. Or either a deeper explanation is that either using both the reference signal and its inverted or inverter carrier signal, separate comparison are made for A side and B side signals respectively, resulting in three possible output levels. The differential output signal is a pulse train with the same polarity as the audio signal and the zero differential output when the reference signal is zero. The common mode signal of the two modulation signal is not zero as for the two-level modulator examples, since the two comparisons are made at different times. NBDS is seen to have severe common mode components around the all harmonics of the switching frequency. Now, NBDS and class BD, since the two legs of each bridge did not exactly complement each other, the signal across the load, which is developed by the voltage at the A switching node minus the voltage of the B switching node does not simply switch between the two supplies. Instead, there is a third state zero differential voltage established when both switching nodes are the same potential, which is never possible in a class AD. One immediate effect of this is that class BD has significant common mode component, while class AD exhibits no common mode voltage. Class BD also requires more precise switching control and can introduce added complexity compared to class AD. And there are several important differences that are observed for the NBDS, where the HES surface shows very pleasant spectral characteristics at lower modulation depth. All high-frequency components disappear at idle. No harmonics of the carrier are present in the output spectrum. The IM components are proportional to M and lower modulation index. Half of the IM components are eliminated. For example, the HES has striped nature. The maximal IM component amplitudes are lower since 3 levels are synthesized, as what I've mentioned that's what the NBDS means at the first slide. There are advantages of NBDS. Sudden degradation incompatible with existing analog facilities offers the most promise for dynamic control, wide control bandwidth, high frequency switching components. In particular, for low or idle input signal, the output contains very little high frequency of energy. For the disadvantages, due to changing width of the pulses, variation in the transmission power is also noticed. More and width requirement is in case of NBDS is somewhat larger than other PWM. And this is also just a diagram that will show you how NBDS frequency domain characteristics shown on the figure. And for the summary, I did discuss to you what's natural sampling, single-sided modulation, 3 levels PD, where we can conclude that it's superior in terms of HF characteristics of the differential output. Unfortunately, the NBDS common mode output contains severe common mode output. And PWM encodes the amplitude of the values of original signals in the pulse width of square wave output. So that is where NBDS came from. So it's PWM, pulse width modulation. And for the third one here, I just mentioned that the main advantage of the class BD or NBDS is that high frequency switching components. Well, thank you for watching and listening. And that's it for this video. See you in the next video. Goodbye.